Good evening, everyone. We will today start with module number 4, which is based on energy management and energy conservation in thermal systems. This is our module number 4, which is dedicated for 10 hours of instruction. And the course outcomes that we are going to discuss in this module is to describe the energy performance evaluation of some common thermal installations and identify the energy saving opportunities. Now, thermal installations, you have come across various thermal utilities like the steam generation system, the boilers, furnaces, waste heat recovery, HVAC, refrigeration, air conditioning. So you see that when we talk about the thermal systems, management of these thermal systems to the optimum use is what about the energy management is all about. So in this course or in this module, we will talk about today's lecture which is dedicated to review of different thermal loads. Then we will see what is the steam generation or steam distribution system. What do you exactly mean by a steam and where it is used? Like we will discuss about the application of steam. Then we will assess the steam distribution losses, where all we can see the steam gets lost in the system. Then also it will cover steam leakages, steam trapping, condensate, and flash steam recovery, and so on in the coming lectures. So whenever we talk about steam, so steam has been a very popular mode of conveying energy since the industrial revolution. So you see, sir, the steam engine came into existence, and then the whole industrial revolution happened, and it changed the entire way of looking at steam. So why steam is more popular is what we are going to discuss in the first 5 minutes. So steam is used for generating power and also used in process industries such as sugar, paper, fertilizer, refineries, petrochemicals, chemical industry, food industry, milk industry, textile. So why we use steam? Because steam has some characteristics. Okay, so what are the characteristics? It has higher specific heat and latent heat. So you see, 2257 is the latent heat of steam at 100 degrees Celsius. When the water gets converted into steam, the latent heat available is 2257 kilojoule per kg. So this much amount of heat we can use it for converting one form of energy into another form of energy in the form of heat. Also, it has the highest heat transfer coefficient. A heat transfer coefficient you have come across. Heat transfer coefficient is nothing but the resistance offered by the heat transfer medium. Okay, and reciprocal of that. Then, whenever we convert water into steam, pipe, and it can be used. That means it can. So that means it is easy to just take a branch out of desired pressure and at desired example. I would like to give you, or when we conduct and visit for an industry, we see that which is at boiler, and that steam is used to convert milk, raise the temperature of the milk to a higher temperature. Okay, and also the same steam which is generated from the same boiler can then be used for washing of crates. Okay, so this way the steam can easily be controlled and distributed, and also it is cheap to generate. Means it's not costly. It will be cheap and to generate the steam, and also it is inert. That means it will not react with any of the other chemically. Okay, so it is called as an inert. So just to recall, what why steam is so popular is steam has higher specific heat and latent heat. Then also it has the highest heat transfer coefficient, easy to control and distribute, and also it is cheap and inert. Okay, what are the thermal load? When we talk about different types of thermal loads, thermal load is the demand for heat energy. The heat may be needed for space heating, hot water heating, or for some industrial process. The thermal load can be served by the boiler, by a generator from which waste heat can be recovered, or by surplus electricity. That means we can use this thermal load to be served by the boiler, or the thermal load can come from a waste heat recovery, or it can come from surplus electricity in the means of heating. So you see the first image is a refinery, is a block diagram for refinery. So steam can be used in refineries. It can be used in some steam, or we can say some chemical industry. So this is the chemical industry. This is the dairy silo, we can say, where the milk is being stored, and then steam can be used in the dairy industry. So application of steam has been seen in wide range of industries. Okay, due to its popularity and due to its the properties that we discussed. So the main property of steam that we discussed is liquid enthalpy. So liquid enthalpy is the enthalpy or the heat energy in the water when it has been raised to its boiling point to produce steam. Okay, and you know at this point that steam can be generated at wide range of temperatures by regulating the pressure. Okay, so water available at 25 degrees Celsius will boil at 100 degrees Celsius at 1 bar pressure. Okay, so pressure is important. At 1 bar, 100 degree is there. And if I increase the pressure, the boiling point will also be increased. Okay, so when it has been raised to its boiling point to produce the steam, and it is measured in kilocalories per kg. Okay, kilocalories per kg or kilojoule per kg, and its symbol is small h suffix f. So hf is nothing but it is a sensible heat, or we can say heat of fluid, hf. Okay, so hf, the heat required to change the temperature of the substance, is called sensible heat. Raise the temperature, just to raise the temperature from 25 degrees Celsius to 100 degrees Celsius. So it will be 75 kilocalories of heat is being, so 1 kg of water in a vessel at 25 degrees Celsius is containing heat value of 725 kilocalories, and is heated by adding much 75 kilocalories more to bring that water temperature to 100 degrees Celsius. So 75 kilocalories is the sensible heat required to change the temperature from 25 to 100. This you have covered in lower semesters. Okay, so enthalpy of evaporation or heat content of the steam. The enthalpy of evaporation is the heat energy to be added to water when it has been raised to its boiling point. So this point starts from boiling point in order to change the phase to steam. So change of phase, there is no temperature change, but there is a change of phase from liquid to vapor. And this amount of heat is called as a heat of or enthalpy of evaporation, or we can say latent heat of vaporization. Okay, so having said this, then what we can say, to change the water to steam, an additional 540 kilocalories would be required. So this quantity of heat required to raise the chemical form of liquid to gaseous state is called as latent heat. Okay, moving further, any difficulty with this understanding of this? This you have covered in lower semesters. That is why we are not spending much more time in that. And this is a popular diagram that we see, which is also called as a phase steam phase diagram. So here you see as the water. So let us say that this is the point. Okay, at which the water is heated from 0 degrees Celsius, 0 degrees Celsius to the saturation point. Okay, so this is the saturation point, which is at 0 degrees Celsius. Its condition follows the saturated liquid line until it reaches the B point. Okay, and that is the liquid enthalpy HF. So by adding the temperature, it will reach up to this point, that is B point. If further heat continues to be added, it changes the phase from saturated steam and continues to increase its enthalpy while remaining at saturation temperature maintained at this point. So temperature remains constant. If I add more amount of heat, which is nothing but HFG, okay, so it will reach at point C, which is a saturated steam line. Okay, as the steam or as the water mixture increases, its dryness, its condition moves from saturated liquid into saturated vapor line. Therefore there are at exactly halfway, if I say this is x, exactly halfway at this point, it is neither water neither steam. So 50% is there. We can say x equal to zero point 0.5. X equal to zero point 0.5 means what? X equal to 0.5 means what? It is either water, if 50% it has water, if 50% it has steam. So this condition is called as a wet steam, or it is a two-phase region. Sometimes it is also called as a vapor. Okay, it is not saturated, it is vapor. So you see, once, so if I ask you that what will be this x value at this point, at B point, what will be the x value? Anybody? 0 or 1?
0, sir.
0. So x equal to 0 at B point, so it is saturated water, and x equal to 1 at C point when it is dry saturated steam. Now by further addition of heat at this point, we'll reach to which point? D point. And this is nothing but the HF plus HFG will become HG. And this, at this point, if I add more heat, then it will be called as a degree of superheat. The steam will become superheated steam, and the temperature at this point at D minus temperature of point C, the difference of this is called as a degree of superheat. T superheat minus T saturated, T sup minus T stat. Okay, this is called as a degree of saturation. And same way, if I add it at different pressures, if I do the same thing, it will create into these lines of constant pressure. So constant pressure lines will be formed, and one point will be reached at which the phase will not be there, phase change will not be there, and that point will be called as a critical point. So critical point is the highest temperature at which liquid can exist. Beyond that, there will be no existence of liquid. There will be no existence of this gray portion. So critical point is a point of highest temperature at which the liquid can exist. Any compression at constant temperature above this critical point will not produce any phase change. Compression at constant temperature below critical point will result into liquefaction of vapor as it passes. So what is the value of this critical point? It is 374 degrees Celsius and 221.2 bar pressure. So always you have to remember, as an engineer, mechanical engineer, you have to remember this value. It is 374 degrees Celsius and 221 bar pressure. Okay. Right. So moving further. So this is a typical steam distribution system in which you have one main steam generator. Main steam generator. This is a boiler, we can say, and from this boiler we will trap this steam. We will collect the steam. So this pipe, this main pipe, is called as a main header. This pipe which is carrying the steam from the generator, steam generator to the system, is called as a steam mains, or it is called as a header pipe. Okay. Now what will happen is the steam distribution system is basically a link between the process and the generator. That means it is the generator and user. Generator and user it is the link between the generator and the user. So user can be anything. Okay, so whatever be the source, an efficient steam distribution system is essential if steam of the right quality and pressure is to be supplied in the right quantity. So right quality means what? At desired temperature and pressure, and quantity means kg per hour. So normally when we talk about steam, it is always given as 10 tons per hour at 200 degrees Celsius. So this becomes the quantity of the steam and the quality of the steam. So in pressure cooker, the volume of the pressure cooker decides the level of water and the quantity to be placed inside the pressure cooker so that the food will be cooked easily. Okay, and all these other dimensions like the vent of the pressure cooker, the whistle, the pipeline, everything will be later on decided depending upon the volume of steam which is generated inside the pressure cooker. You understand this? So, steam distribution system is what we are learning, and the steam distribution system is link between the user and the generator. Okay. Right. So, because the quantity and quality of the steam is very important, installation and maintenance of the steam system is also very important issue and must be considered as the at the design stage. So, whenever you are designing any process, designing any steam generation system, the steam distribution system should be considered at the design phase. Okay, so why a steam distribution system is very important is that when the steam flows or passes through the pipe to the distribution system, it tends to get condensed. And whenever we say condensate will be having a lower volume than the steam, and because of that, there is always a driving force. Because of condensate, there is a driving force for the steam to move from one point to another, but this condensate is not applicable or not useful to us. Why? Because we are spending a huge amount of energy for converting water into steam, and when this steam passes through the distribution system, it condensate, and condensate is not the final result that we get, that we want to have. We want steam at the end, and condensate is a byproduct, so it is a loss. Okay, so the steam generated in the boiler must be conveyed through pipe work to the point where its energy is required. Okay, so the steam mains and these are other will be called as a branch steam branch pipes. Okay, right. So in this, what all things are required for the design stage? The working pressure. Very important point is the working pressure. So the distribution pressure of the steam is influenced by a number of factors. Example, the safe working pressure of the boiler. We cannot keep it too high or we cannot keep it too low. If we keep it too low, then condensate will form at the starting itself. If we keep too high, then we have to increase the diameter of the pipe. Increasing the diameter of the pipe will cause increasing the cost of the pipe. Also the weight of the pipe. The system becomes bulky. So when the pipes are heavy, the flanges which are required to hold this pipe will also be costly. Okay, so structure will also be costly. So we have to find an optimum point at which the steam should be maintained at a proper working pressure, not too high, not too low, and the also one has to talk about the minimum working pressure so that the loop will be completed. Okay, it will again reach to the starting point, so that loop also to be completed. So minimum pressure and working pressure, these both things are to be considered while considering the design phase. So why we are considering the high pressure is to be maintained? Because the steam has to overcome the frictional resistance offered by the pipe. Okay, then we have the condensation within the pipe, right? Therefore, allowance should be made for this pressure loss when descending upon the initial distribution pressure. Okay, having determined the working pressure, the other factors that are to be considered while designing are the general layout, pipe sizing and design, pressure reducing and desuperating station, air venting, and steam pipe insulation. All these parameters also prove to be helpful when we are going for designing of a steam distribution system. Before we go into that, we will look at one numerical in which we will see how the velocity of the pipe decides the diameter of the pipe. Okay, so you see the a process requires 5000 kg per hour. This is the quantity of dry saturated. This is the quality at 7 kg per centimeter square. So quantity and quality of the steam is are given. For the flow velocity not to exceed 25 meter per second. That means the velocity of the steam is fixed at 25 meter per second. Determine the pipe size. How to go about such a problem? The very important problem. Most of the time it is used. It is asked in the final year exam. Okay, so you see flow velocity is given, specific volume you can find out from the steam table at 7 kg per centimeter square. So it is zero point 0.7 bar pressure, it is 0.24 meter cube per kg. Okay, mass flow rate given 5000 kg per hour, or we have to convert it into 1.38 kg per second. Volumetric flow rate, it is given by mass flow rate into specific volume. So it comes to around 0.33 meter cube per second. So we know the formula for volume flow rate is what? Is cross-sectional area is given by volumetric flow rate upon flow velocity. So pi by 4 d square will be equal to volumetric flow rate upon flow velocity. And if we solve for d, we get diameter as 130 mm. So this is how we can determine the pipe size if the velocity or other parameters are given. So very important. We can. I will wait for say 2 minutes for you to take down this, or take a screenshot of this, and later on you can write it down in your book. So moving further, we will now discuss one by one about the general layout, pipe sizing and design, pressure reducing and desufflating station, air venting, and steam pipe insulation. Starting with general layout, what is general layout? General layout and location of the steam consuming equipment is of great importance in efficient distribution of steam. Why? Because steam pipes should be laid by the shortest possible distance rather than to follow a building layout or road, etc. So I would like to tell you here that which particular setup is efficient for moving the steam from one point to another, whether it is a square cross section or a circular cross section. Can anybody tell me which cross section is more preferred, whether it is the square one or the circular one for easy movement of the steam? Anybody?
So circular one.
Circular one, yes, very good. Because see, whenever the circular bends are there, the frictional resistance is lesser for a circular diameter. Okay, and when you look at, but the area being wasted is much more, because whenever we have the room size, always a room will be given in a square dimensions. So movement of this pipe from the square room with a circular cross section will waste a lot of more amount of area for movement of this pipe. You're understanding what I'm saying? So for that we prefer as a square duct. But whenever we are making a square duct, it is the optimum value which is given in the handbook, that the minimum curvature which is to be maintained whenever we are putting a steam generation system for a given diameter of the pipe, this should be the curvature in order to reduce the frictional loss. FL V square upon twice GD. Okay, so this FL V square, that L, it depends upon the L. It also depends upon the diameter of the pipe. Okay, so general layout is very important. Okay, then steam pipe sizing and design. So any modification or alteration in the existing steam piping for supplying higher quality steam at right pressure and quantity must be considered for following points, which is the pipe sizing. Important thing, pipe sizing for superheated steam will be 50 to 70 meter per second, the velocities. And you know, by velocity, if I know, then I can calculate the diameter of the pipe. So velocity should be fixed. For superheated steam, you make a note that 50 to 70 meter per second should be the preferred velocity. Whereas for saturated steam, if you are moving saturated steam, then it should have 30 to 40 meter per second velocity steam. And for wet or exhaust kind of steam, 20 to 30 meter per second. So 20 to 30 for wet steam, 30 to 40 for saturated steam, and 50 to 70 for superheated steam. Okay, so why this pipe sizing is important? Because of the frictional effect, we can have the pipe sizing, and also we can have the design, that is whether it will have circular cross section or square cross section and so on. Okay, and then we have seen the numerical, which is where we can calculate the pipe sizing based on the velocity. So in practice, whether for water pipes or steam pipes, a balance between the pipe size and pressure loss should be maintained. Okay, the steam piping should be sized based on permissible velocity and available pressure drop. Okay, but it is seen that a pressure drop change will be inversely proportional to the fifth power of the diameter change. So if there is a 1 unit of diameter change, the fifth root of pressure will change will take place. Okay, so this you have to remember, that pressure drop is inversely proportional to fifth power of diameter. Diameter increase, pressure will decrease by how much? By fifth root of power. Okay. Then pressure reducing de-superheating station. So a reduction in steam pressure through a pressure reducing valve is which process? It is an isenthalpic process. So saturated steam when reduced to lower pressure results in superheated steam. Okay, since the process requires only saturated steam, desuperheating is often required to compensate for superheat gained in pressure reducing valve application due to isenthalpic expansion. So pressure reduction and desuperheating of the steam or conditioning of steam is done in many industries or processes. Okay, so generally the temperature of the steam after desuperheating will be closer to saturation temperature for heat transfer application. And there are various methods by which we can have desuperheating. What are those methods? It is just spraying of water through nozzle can cause a desuperheating. Okay, so and most of the industries nowadays are installing automatic control for desuperheating. But desuperheating, if the steam is superheated, it can cause many problems. So desuperheating is very important, or pressure reducing is very important for that. Then air venting. What will happen if the air is not vent? The envelope that is holding the steam can burst. So there should be proper, if the pressure increases, the required amount of pressure can be maintained by providing air vent. So air vent are also statistically designed so that whenever the pressure reaches that point, the air vent will be automatically on. Okay. So automatic air vents are operative in some of the industries. Right. So, and what about steam pipe insulation? So everyone will agree that insulation is must. Okay, for covering the pipes and steam consuming equipment, because it can retard the flow of heat from system to the surrounding. It can reduce the flow of heat from the system to the surrounding, and if we are able to reduce the heat loss from the pipe to the surrounding, condensation will not be there. So condensation can be minimized by using this. So it is normally seen that the purpose of steam pipe insulation is to conserve energy by reducing heat loss, to facilitate temperature control of the process, prevent condensation of steam, prevent or reduce damage to pipe from exposure to and control surface temperature for personal protection and comfort. Okay, so these are the points for which the steam pipe insulation is required. Okay, so now let us look at the assessment of steam distribution losses. So from where the steam is generated and how the losses will take place. So this is the fuel. The fuel can be any fuel. Okay. So you see that the fuel will come. Let us say that 100% fuel is utilized in the boiler, and the boiler will convert 80% into useful amount of steam. Okay, so here 20% of the heat is lost in the boiler. Then the steam will come in the mains, steam mains. Okay, so steam mains there will be 5% losses in the steam main header pipe. Then the 75% will go into the process. Process will utilize all its steam, and 25% will be lost to the atmosphere. Out of which 30%, 35% will be going to the product, and then 15% will be from the process. It will go to the condensate, because during its process it is converted into condensate. So condensate return system, there is also another term which is called as a condensate recovery system, in which out of this 15%, 10% will again sent back as a feed water, hot feed water, as a condensate. Okay, so you see that overall, if I see the efficiency of the steam distribution, then the overall efficiency is only 35%. Okay, so you see how much is the losses, and in order to address these losses, there are several things that we can do. So let us go one by one. So these are the efficiency improvement in steam distribution system. So which is one of the equipment is called as a thermo compressor. What is thermo compressor? So what happens, in steam utilization equipment, where condensate comes out at very high pressure. So condensate is there, it is water, but it is at high pressure, which cannot be used in a process, okay, or in a product. So the major portion of it flashes into low pressure steam, which goes wasted. That means entire amount of condensate is not recovered from the point. Okay, you understand that the pressure cooker is there. Pressure cooker will generate steam, and when it passes through pipe, there is a condensate is there. But condensate, if you put it in the open air, what happens is that condensate, when it comes in contact with atmospheric air, there is a pressure drop is there, and it gets converted. The condensate gets converted into flash steam because of high pressure, and then there will be no condensate. It will be flash steam. That means low pressure steam. And this low pressure steam is of no use to us, because it will not have any temperature, or it will not have any pressure. So this flash steam you can observe when you take a bath with hot water, and when the room is closed. You come out of that room and somebody else enters. There is no hotness in that room, but there is all the droplets of the steam is there. That is called as flash steam, which is of low pressure and low temperature. Okay, you understand, right? Right. So you see, using a thermocompressor, it becomes feasible to compress this low pressure steam by high pressure steam, and reuse it as a medium pressure steam in the process. So what will happen? See, the low pressure steam will be taken in by the thermocompressor. It will be compressed by this high pressure steam from the system, and as a result of this, it will be mixing in the mixing chamber. It will become a medium pressure steam, and this medium pressure steam can be again used to different process utility. Are you getting the idea? Okay, so this is the beautiful feature of the thermocompressor. The thermocompressors are designed to accurately mix lower pressure steam with higher pressure steam. The higher pressure steam moves is the motive steam enters the low pressure steam and increases its pressure. The motive steam is introduced through a nozzle of the compressor. As the nozzle opens, the high velocity motive steam draws the lower pressure into the thermocompressor body. An exchange of momentum across the steam are mixed, and the mixed steam is accelerated to high velocity with a uniform profile in the mixing chamber of the thermocompressor. As the mixed flow enters the diffuser section, the diffuser flow area gradually increases to allow the velocity of the mixed flow to be reduced. As the velocity is reduced, the steam pressure increases because it is inversely proportional. And at the end of the diffuser, the discharge pressure is higher than the lower pressure suction flow entering the thermocompressor. As a result of what will happen, we will get a medium pressure steam, which we can use it in the process utility. So what are the advantages of thermocompressor? So no condensation losses takes place. Thermal efficiency of the system is high because there is no movable parts, so no operation, no moving parts, so maintenance is free. Low space requirement because it is vertical and very streamlined. It is having very low space requirement. Insensitive to fouling because there is no water involved. It is only steam happening, so no fouling will take place, and it can have high operating reliability. Okay, so this is the peculiar feature of a thermocompressor, which is improving the efficiency of the steam distribution system. In order to reduce the condensate, we can have this kind of okay. The other device which is used to increase the efficiency of the steam distribution system, I am talking about steam distribution system and not steam system. Efficiency to increase the steam system is related to boiler. So boiler efficiency improvement. I am talking about once the steam comes into the distribution system, all the pipes, how to increase the efficiency of the steam distribution system. So another component is a dryer. Okay, so drying is a process by which a liquid or we can say water is removed from the material. Okay, this is usually applied by achieved by applying heat, typically steam or a carrier gas through or over the surface of the material. The objective of drying is to form a product that meets the water content specification. So the amount of water removed depends upon the desired product. Okay, the basic drying energy requirement in the latent heat needed to evaporate the water. Clearly, this depends upon the amount of water being evaporated. So in most cases, the product material, the carrier gas, and the equipment also need to be hot so that the total energy required includes heat leaving the dryer in the exhaust flow. Okay, then this includes the latent heat of water being evaporated, but the sensible heat of the hot gas can be significant. A heat loss from equipment and ducting, however good the insulation, there is always some heat loss is there. Okay, then heat leaving the dryer as a hot product and the motive power for fans and conveyors to suck in the steam which is there, which is having some water content in it. Okay, so this is how the two components will work. So in the next lecture, we will talk about the steam leakages. Okay, steam trapping. Okay, so this steam leakage, steam trapping, we will discuss in our coming lectures. So just a quick summary that what we have done up till now. We have started with course outcome number 4, which is a module 4 in order to have the performance evaluation of some common thermal installations, and we have started with steam. So steam is used for achieving the thermal load or satisfying the demand of heat energy. It can be for space heating, for hot water, or for some industrial processes. It can be used in many of the industries like sugar industry, textile industry, food industry, refineries, then petrochemical industries, then process industries, food industry, milk industry, and so on. And properties of steam includes the enthalpy of the sensible heat and the latent heat. We talked about latent heat having more heat. So steam is very popular because it is easy to control, then easy to distribute. It is ideal. It is inert. It is not reacting with any other component. Then we can control the flow of steam. Quality and quantity can be maintained. Also, it is cheap method of producing the steam and so on. Then we discussed about the steam phase diagram, in which we talked about how this curve is drawn and what are the different types of constant pressure lines. And we discussed about dryness fraction. Then we talked about the steam distribution system, which includes the steam mains or steam header, and then there are the branch. And during its journey from the generation to the user, the steam distribution system appears to be a link between the generator and the user. So during its journey, when the steam passes to the steam header and the sub branches, there is a drop in pressure due to condensate, due to which the condensate takes place. And there should be a mechanism to collect this condensate and then circulate it back to the generator in order to have the best efficiency of the steam distribution system. There are assessment of steam distribution losses should take place by providing some general layout must be studied at the design phase. Then we have to look at the pipe sizing, then the cross section, then pressure reducing or desuperheating, air venting should be done, and then insulation should be there. Then we talked about what are the various losses that happen during the steam distribution system and how to recover that. We have two devices, which is thermocompressor and the dryer unit in order to increase the efficiency of the steam distribution system. Okay, so we will stop here. If you have any difficulties, you can ask me now.